In this video, we talk about the percent yield of a reaction. In all stoichiometric calculations that we have dealt with until now, the leading approximation is that the reaction went to 100% completion, and then you could predict exactly how much product you would get from a given amount of reagents. But in reality, when you go to the laboratory, rarely you get 100% completion. In reality, what happens is that what you predict you will get is always going to be greater than what you actually get. Now, there's very many reasons for this to happen. One of them is that, well, some reactions actually have side reactions, right? So when you put the reagents together, those reagents will lead to two sets of products, and you're only interested in one. Okay, that can happen. Or maybe the reaction rate is very, very low. That means that the reaction is very slow. It takes a long time for the reaction to complete, and maybe you're collecting products before the reaction is over, right? So there's many reasons why you might not get all of the product you expect. Right, so in this video, we're actually going to run a problem to quantify exactly how we talk about what you should get versus what you actually get. That is actually defined by what we call the percent yield, and the percent yield is very simple to define. Right, so the percent yield of a reaction is equal to the amount, we can say the theoretical yield if you want, theoretical yield over the actual yield times 100%. The other way around is the actual yield over the theoretical yield times 100%. Okay, so what you get over what you expect multiplied by 100%, so you'll get a percentage of yield that you have obtained. All right, so let's run here a numerical example to illustrate this concept. The reaction that we're going to be talking about is calcium chloride in aqueous solution reacting with sodium carbonate, also in aqueous solution, to generate calcium carbonate, which is a solid, and then sodium chloride, which is in aqueous solution. Balance the reaction, we need a stoichiometric coefficient of 2 in that product sodium chloride. All right, so we start the reaction with 10 grams of this species, and then 9 grams of this species. And what we actually get in this product, this is the one that we're interested in, is 6.02 grams. Right, so there's various things that we have to do here. First, we have to determine what is the limiting reagent of these two, because we don't know if these are mixed in the correct stoichiometric amounts. And then we'll have to calculate how much product we're missing. We can calculate how much product we expect from our regular stoichiometric calculations, and then we will compare it to what we've actually measured, with what we've actually weighed, and then that will give us the percent yield. All right, so this is a problem of limiting reagents. I'm going to do each one of them in tandem. Remember that to figure out what reagent is limiting, what you do is you calculate the expected number of moles of the product of interest for each one of the reagents, and then the one that gives you a lower amount of moles, that will be limiting. Okay, so for calcium chloride, what we need to do here is transform to moles. So 1 mole of calcium chloride, you need to divide here by the molar mass, which is 111 grams per mole for calcium chloride. Okay, and up to here you would get the number of moles of calcium chloride. We have to do the stoichiometric conversion to calcium carbonate. Okay, but there's 1 mole of calcium carbonate for every mole of calcium chloride, which is what we have until here. So this will give us directly the number of moles of calcium carbonate. And that number happens to be 0.0901. Okay, that will be the number of moles if calcium chloride was limiting. We can do exactly the same calculation for sodium carbonate and see if this is the limiting reagent. And so we calculate first the number of moles, dividing over the molar mass. The molar mass of sodium carbonate happens to be 106 grams per mole. So this gives us moles of sodium carbonate, and then we do the stoichiometric calculation, right? So there's a 1-to-1 relationship between the moles of calcium carbonate and sodium carbonate. So that is going to be 1 mole of calcium carbonate over 1 mole of sodium carbonate. And when we do this calculation, we find out here a result of 0.849 mole of calcium carbonate. Okay, comparing the moles obtained with each one of the reagents, we realize that sodium carbonate happens to be the limiting reagent because it's the one that gives you the lower amount of product. Okay, so this one is limiting. And then if we assume that the reaction goes to 100% completion, then we can transform those moles of calcium carbonate to grams, to mass of calcium carbonate, and then figure out what the theoretical yield should be for this reaction. Okay, so we can do this in a different row. 0.849 moles of calcium carbonate expected, and then we simply have to transform this to mass by using the molar mass. Okay, and the molar mass of calcium carbonate happens to be 100.09 grams of calcium carbonate for each mole of calcium carbonate. Okay, moles goes away with moles. And then that is going to give me grams, which is 8.50. Okay, this is the theoretical yield. That's the mass of calcium carbonate that I expect if the reaction goes to 100% completion. In reality, we're not obtaining this mass. We're obtaining a little bit less, which again, this means that, well, maybe you've lost something in the way, or the reaction has a side reaction, or again, there's been some other source for decrease in that yield that you expect. Okay, but we can quantify the percent yield by actually calculating it, right? So the way to calculate it again is the percent yield is what you, the actual yield over the theoretical yield. The actual yield is 6.02 grams. The theoretical yield is 8.50 grams. Multiply by 100%. To obtain 17.8%. Okay, so this video has illustrated the concept of the percent yield.